Hello. So let's start by reviewing the sample exams. Uh, so in my box drive, in the sample exams folder, I put in the sample exam and also another document, toy example complete, which I'll discuss today. So the sample exams will be mainly short answer questions and multiple choice questions. So for example, the attack named the mobile buy targets which type of sensor? So it's a camera. Can ASIL-D system be composed of multiple ASIL-B subsystems? Yes. This is called ASIL decomposition. In PID control, which terms can be used to eliminate a steady state error? That's the integral term. So by integration over a recent history, you can eliminate the steady state error. True or false, Twiddle for PID controller tuning can be viewed as a form of reinforcement learning. It's true because it learns from the reward signal, which is the cumulative deviation from the ideal trajectory, and uses that signal to update your PID parameters.
Sorry to interrupt, Songguo.
Sure.
Yeah, I have only like 10-15 minutes to join. So I just ask if there are some questions for me regarding the labs or for the area. So please send them now. I did put a notice in the discussion forum, but I haven't seen it. Send it as mail, at least not to me. Maybe you got it.
So the last assignment is not obligatory. I wonder if people are interested in working on it. I guess everyone is busy at this time.
Yeah, I guess they prioritize the exam questions.
Yeah.
So don't hesitate to ask anyhow if you have some questions. But yeah, sorry to interrupt.
Sure. So do students have any questions on the lectures given by Caleb on the, there are 4 lectures, DRL 1 to 4. Any questions on those before he leaves?
Everything is crystal clear. Nice.
Yeah.
Okay, I will be here for another 10 minutes, so let's
Sure.
continue. Yep,
Sure.
thank you.
Yeah. Yeah, no one asked any questions online either. So,
no, it's
yeah.
kind of sad.
Yeah, so for Twiddle, I mentioned it in the slides also. So, yeah, I said it that Twiddle, did I say Twiddle somewhere? Oh yeah, the reward function part. So Twiddle learns PID parameters, but it's very crude because it only uses the binary feedback. Error is less than best error or not. If less than best error, then you do one kind of update. Otherwise, you do another kind of update. So ideally, you should measure the magnitude of deviation from the track, and then maybe update the parameters proportional to that magnitude of deviation. And that's more reasonable. But this one is simply a binary feedback. Well, maybe not that reasonable because the relationship between the PID control parameters, PID, and the eventual cross-track error is very complex, right? It's highly nonlinear. You need to run a whole bunch of steps and then accumulate the errors. So it's not obvious at all. You have dynamics in it. You have the bicycle model in it. So it's not a straightforward linear relationship. So maybe the binary feedback is okay. It's just a heuristic anyway. So why does AlphaGo not use tabular RL such as tabular Q-learning or SASA? It's because the state space is too large. I think it exceeds the number of atoms in the universe. So you must use function approximation with deep neural networks. So function approximation, you can use simple linear functions with a linear combination of features, like I mentioned last class, or you can use nonlinear functions such as the deep neural networks. So what's the probability of selecting one of the non-greedy actions in state S in epsilon greedy action selection if the total number of possible actions is n? Is 1 minus epsilon plus epsilon divided by n because the extra term comes from the epsilon greedy selection definition. So
In fact, Zunghua, I remembered a question to ask to Mr. Kali.
sure.
Yeah, Mr. Kali, for end-to-end learning, it's learning for PilotNet by using feedback from a camera that captures the images combined by data being collected from the driver who's maneuvering the car around different obstacles, right?
Well, the learning is mainly from, if you talk about the lab 5, it's from the number of tiles you drive over. So you, as the driver, select the turning and braking and so on.
I meant, sir, regarding end-to-end learning in PilotNet, this is the methodology. You have a camera which films, and you have devices to collect the movement for which the driver is maneuvering, and the system has to imitate or learn from the from
a human driver or something.
Yeah, the human driver. Now, exactly what is mid to mid in this case?
I think this is Songwa's area, as I understand. Sorry, but usually there's a problem with that because the driver selects something which might not be good in another very similar situation. For instance, in a forest machine or something, it depends on the history. Maybe they have to slow speed, it's slippery and so on, and the next situation is not slippery, and then.
In fact, in the website of NVIDIA, they were speaking that PilotNet was really good. There are things that were not coded, yet the system managed to distinguish them, like the grass on the sides of the road, or the bottom parts of cars. The system managed to recognize them as it has to avoid these obstacles or these features, although it wasn't intended in the coding, but the system managed to do so unintentionally. So in that web page, they were speaking about this methodology and its merits. But I tried to look for something about mid to mid for more clarity about it as a concept, and I couldn't understand exactly.
Yeah, I don't know. I haven't read this paper, but mid to mid. Anyhow, you need to learn from something. So if you learn from a driver, then you have some kind of imitation learning or something.
True.
But this mid to mid, it depends if you have some kind of feature signal which you can learn from, if it's going good or bad, as traditional reinforcement learning. But I don't know the architecture of this. Maybe Songa knows.
So PilotNet is end-to-end. So are you
True.
talking about some other work on mid-to-mid?
Maybe SuperNet is mid to mid, right?
Yes.
So what is mid to mid exactly, Mr. Xungwa? Because on the internet, there isn't really that much clarity about this term. What does it mean? What I understood about end-to-end is that as imitation learning, you have the camera, you have like a window which unboxes what the camera is concentrating on, while you are, and while that there is a driver who's driving, the movements he's taking are being recorded and synchronized with what the camera is picking. And this is how the system really learns how to drive. But in mid to mid, exactly, in simple description, what is mid to mid?
Oh, the inputs, outputs of the machine learning part is different. So for PilotNet, you need to instrument the vehicle to collect the throttle and steering. On the right-hand side, you need to collect throttle and steering. But for ChauffeurNet, you don't. You simply collect vehicle trajectories and rely on a low-level controller to follow, to track the trajectory. On the left-hand side, the machine learning model does not deal with the raw camera image data. It deals with the intermediate representation of the bird's eye view. That's been processed by a perception module. So the perception module is separate. Maybe it's based on point cloud processing, maybe not even machine learning. Likely it's based on deep learning from images merged with point cloud processing for LiDAR. But the machine learning model does not deal with the pixels.
I see.
So on the left-hand side, you have a more abstract image of the surrounding environment in the form of bird's eye view. On the right-hand side, you have a more abstract output in the form of trajectory, not throttle and steering.
Okay. Okay, that is a clear distinguish between the both methodologies.
Yeah, yeah.
Thank you very much indeed.
Good idea.
Sure.
Yep. So I have to leave now. Bye bye and good luck.
Thank you.
Bye bye.
Bye.
So coming back to this question, I think you remember this, right? Simply because you need to develop the epsilon among the n possible actions, including the greedy action. So you have the extra term here.
But sorry, Songa, wouldn't this answer be for the greedy action?
One of the, oh, sorry. Yeah, should be selecting the greedy action. Yeah.
Okay, great.
Assuming there's only one, because that may be multiple if they have equal action values. What's an episodic task? It's a task that has a limited number of actions and then ends, as opposed to a continual continuous task that never ends. So yeah, that's pretty clear. So for the following MDP, you have a state in the center. That's the goal state, and it has because you can view it as leading to another separate terminal state with reward 0 and ends the episode, or you can view itself as a terminal state, depending on your point of view. So this guy has a value and Q value both equal to 0. So any action costs you -1 reward. So the goal of the agent is to get into the goal state as soon as possible to minimize the minus to maximize the reward and minimize the number of steps spent in this maze. So suppose the agent, first of all, this is a MDP, not a POMDP. So the agent has a GPS on him. He knows exactly where he is. That's the implicit assumption. And then he moves from state 3 to 2, and then back to 3 and to 4. And assuming gamma, the discount factor is 1, alpha is 0.5, and show the state value, action value function, and action value functions after salsa and Q learning. So TD update is the current state bootstrapped of the next state's value function. So the next state is initially 0. So V3 bootstraps of V2. So and then it gets minus 0.5, and then V2 bootstraps of V3 because you always bootstrap off the state you are moving into in the next time step. So initially you are moving from 3 to 2, so you bootstrap V3 off V2, and then you come back and move back to 3, and then you bootstrap V2 off of V3. And then V3 goes into V4. So and then this bootstrap is accurate update. Well, it's based on V4, which is accurate. But for the previous two, they are really bootstrapping is called a guessing based on another guess. So only V4 is the ground truth, has a ground truth value of 0. Hopefully, this ground truth value will propagate through the update process to the other states. For salsa, you have a larger table to maintain. So you have state 3, you have left or right. -1 is left. +1 is right. And you update Q3 -1 and Q2 +1 and Q3 +1. So in this case, V3, in the previous TD case, V3 was updated to be -0.5, but in here, the Q3 +1 has no relationship with Q3 -1 at all. So the previous value of updated value of -0.5 for Q3 -1 is not useful for updating Q3 +1. So moving left experience does not help with the Q value function for moving right. So everything is a 0 in the update equations. You get -0.5 for all the Qs. For Q learning, The only difference is the max here. So at every next stage, you got to look left and right and pick the largest Q value. But in this case, the Q3 minus 1 is updated to minus 0.5. So Q21, which moves into 3 in the next step, has the max term here. So so it takes the max of minus 0.5 and 0. So it has the same effect as the SARSA update. So for SARSA update, you go from 2 to 3, and you're trying to update Q21 with Q31, but Q31 was never taken before. You never moved right from state equal 3. So that's 0. And then for Q learning, when you're updating Q21, you must look at state equal 3 and look at the two actions, left and right. So left was updated to be minus 0.5, and right was not updated, it's still 0. So take the max. So the fact that Q3 minus 1 is minus 0.5 does not affect Q learning, because it only looks at the best Q value among all the action choices. Then I spent a long time to expand on this example. So if you go to my box drive, in the sample exams, I worked out this example in its full glory. So now I only care about the left part of this chain. So I removed the right part. So on the right, you have a single terminal state, and then from state equal 4, you always go into it with a reward of 0. So that's the essentially the same MDP, except only with the left part. So, and also I set alpha, the update weight, to be 1. That is, you always replace your V or Q value with the latest update, with no memory of the past. So that's an extreme case. And gamma, the discount factor, is also equal to 1. All value functions are initialized to 0. So first use policy iteration, value iteration to derive optimal policy. So here's the policy evaluation. So you start from the uniform random policy, and the Bellman equation says you average over all possible next states, and then average over all possible actions from the current state. So if you remember my lecture on MDP planning on this example, so it's helpful to draw this Bellman backup tree while you are doing this update. So if it's a deterministic environment, the lower part of the update tree has branching factor of 1. The upper part is dependent on how many action choices you have. In our case, it's 2. So from 1 going left, you have the Q1 left is minus 1, the current reward, plus the value of the next state, 1. And 1 going right, you have this equation. So remember that going left in state 1 keeps you in state 1. So for 2, left goes to 1, right goes to 3. For 3, left goes to 2, right goes to 4. And then you have a set of linear equations. you can solve for this equation to get -12 for state 1, -10 for state 2, -6 for state 3. It's also reasonable because state 3 is closest to the goal. So it should have the highest value function. For policy improvement, you take the argmax of the action among the Qs for a given state. So the Qs are derived as part of the process when deriving Vs. So you have the correct actions only after the first iteration of policy evaluation followed by policy improvement. So because -11 is higher than -13, you should move right in state 1. And similarly for states 2 and 3. Just to be sure that the policies are stable, you go another round and evaluate the policy and you get another set of linear equations, and now you have these set of values. So it's very reasonable because from state 3, you can go into the state 4 with 1 step, so it should be -1. From state 2, you can go to state 4 in 2 steps, so its value is -2. So that's a very reasonable assignment of value functions. And then that's for the last policy derived in the first iteration. And then you plug in the new get the new Q values. So you take the argmax and get the new policy, and it's the same as the previous policy. So the policies are stable. So in this case, the value functions happen to have also converged. So in fact, you can set up a set of linear equations involving all the Q's without the V's at all. So that works too, but the equations are larger. So and then we did not discuss it in class, but you can use a value iteration to derive the optimal policy. So I think we did not, at least we did not give an example. Policy, yeah, we only discussed the policy. Value iteration, we do have value iteration. Okay. All right, I remember now. Yes, it is the solved with iterative value iteration. So in this toy example, yeah, you can, in general, you may iterative solving method. So there's no general method. For example, MATLAB. With MATLAB you can solve a set of linear equations easily, but for the equations with the max operator in the middle, you cannot really solve it easily. So you need to iterate. But in any case, by observation, you can see the optimal value functions here. So let's look at TD learning for this a bunch of episodes. So the episodes are: first, you go from 1 to 2 to 3 to 4, 3 times, 3 episodes of this movement, and then you follow it by 5 episodes of 3 to 1, 2, 3, 4. So you go left and then right. Left, yeah, especially when you are in state 1, you go left again. So you have 1 left minus 1, and then 1 right. So for this sequence of 8 episodes, what happens to the value function if you do a TD learning? So I worked out the equations. It's interesting that this never converges. That's kind of unexpected. So because the mainly after first 3 episodes, everything still looks normal. So V1 is -3, V2 is -2, V3 is -1. So if we stopped there, then everything is perfect. But then you do another few episodes. From V3, you bootstrap off of V2, and you see V2 has -2, and then V3 is -3. So it shouldn't be -3, but because I have this very large alpha is 1, so it just updates the new V3 and forgetting about the past completely. So V2 is bootstrapped off of V1, and V1 is bootstrapped off of V1 itself, and V1 is bootstrapped off of V2, but previous V2 was -4, so it causes V1 to be -5. So eventually, when you reach state 3, you get the ground truth value of V4 of 0. So it gets the value of -1. So this is good. However, after this step, the episode ends. So this -1 never had a chance to propagate to the other states. The other states have very minus values. And then if you go to another episode, it only makes things worse. The values just keep getting more and more negative. So I think it's because of the particular choice of the episodes. That is from 3 you go left, and then right, and then you end at 4. So the only correct value of V3 equals -1 was never had a chance to propagate. So if you can move from 3 back to 2, back to 3, back to 2 a few times, maybe things will converge. So in the textbook, it mentioned the optimality of TD0. So it says that TD0 will converge to the optimal value. So any fixed policy pi TD0 has been proven to converge to V pi in the mean for a constant step size parameter if it is sufficiently small, and probability 1 if the step size parameter decreases according to the usual stochastic approximation conditions. So it has a convergence proof. But for this example, even if you reduce the step size alpha, I think it doesn't really help because these steps of 3, 2, 1, 2, 3, this round trip, left and then to right, really decreases all the value functions. So yeah, I'm not exactly sure how to explain this, except to say that it's the episodes are not very representative. If you have sampled the episodes from a random policy, I'm sure the value function will converge. So that's my comment on this phenomenon. So when moving left, V3 bootstraps off of V2, V2 bootstraps of V1, and so on. The sequence of TD updates cause all value functions to be increasingly negative. So moving right helps to set V3 to the correct value of -1, but then the episode ends immediately. So V1 and V2 do not have a chance to bootstrap off the new V3. So if the episode does not end immediately, but goes back to the left again, and then V1 and V2 will have a chance to bootstrap off the new V3, and they will converge to the correct values. So that's just explanation for this particular sequence of episodes. How to reconcile this with that theorem, this convergence theorem of TD0, I'm not really sure. So in any case, TD cannot be used to learn a policy in the model-free case. So in my overview diagram, so TD and TD lambda I did not discuss. It can only be used for prediction, for policy evaluation. It cannot be used for control, cannot be used to compute the optimal action because it doesn't have the Q values. SARSA, Q-learning, expected SARSA, and Monte Carlo control, they can be used for control. So for SARSA, I worked out the Q values. So here they are. So the Q values for the right movement look very reasonable. So for moving right, you have the optimal, essentially optimal Q values, -3 for state 1, -2 for state 2, and -1 for state 3. But the action values for moving left look unreasonable. So Q1 left is a -4, Q2 left is -5, and Q3 left is -6. So the reason, the explanation is that the only trajectories in the training set for moving left actions are 3, 2, 1, 1 repeated, and 2, 3, 4. So the Q values are updated based on only on this trajectory. So from state 3, take action on left, it can only take the above trajectory and reach the goal in 6 steps. So SARSA just learns this Q value to be -6. So it's on policy. So it's yeah, here is where the on policy part comes in. So it can only learn from the trajectories it experienced. So however, even though the Q values for the left actions are not accurate and too pessimistic, the greedy policy is still optimal. So if you take the arc max among the in state 1, you have -4, -3. So right action is better. In state 2, you have -5, -2. So right action is better. And in state 3, you have -6 and -1. So the policy derived from the SARSA learning is still optimal, but the value functions are wrong. So that shows that policy often becomes stable long before the value becomes accurate. That's what motivates the policy gradient and other policy-based IR methods. So that's SARSA. And then for Q-learning, I worked out the equations, and now it looks good. So for all the first, for the right actions, all the Q values are okay, -3, -2, -1. For Q1 left, -4, that's also good, because if the agent moves left in state 1, then follow the optimal policy of moving right, then it takes 4 steps to reach the goal. 1, repeat it, 1, 2, 3, 4. So its cost should be -4. There's no other way of getting a higher cost. So Q2L is -4 because the shortest path is 2, 1, 2, 3, 4. So a Q3L is -3 because that's the path is 3, 2, 3, 4. So the Q values obtained from Q learning are accurate. So Q learning is smarter than SARSA. Since it's off policy, agent can learn the correct Q value functions that correspond to trajectories that it has never actually experienced. So the agent never experienced the trajectory 3, 2, 3, 4 in the training set. But the agent's Q value functions are updated based on this trajectory. Not exactly, it's based on the max operator, but looks like it's based on this trajectory. And because the Q values learned by Q learning are accurate, and obviously the greedy policy will be optimal. So if you take the max among the left and right actions, so a max is right action in state 1, right action in state 2, and right action. So the policy is, greedy policy is also optimal. So I think this example nicely illustrates the differences among the different methods. So I hope you can go back and work it out, the details. If you can catch any errors in my derivation, I'll be very glad. So obviously, I won't give you such a large exercise in the exam. It took me almost a day to work this out. So, but I may give you a similar, smaller scale questions to test your knowledge on the basic concepts of the first the policy and value iteration methods, and then the SARSA and Q learning. So a TD learning is just, or SARSA is just TD for Q value function, and TD is TD for V for the state value function. These two are essentially only differ in the V and Q. They are both on policy. So any questions? So yeah, for the Q learning, if you look at the learning process, it's quite gradual. So it doesn't reach the correct values in one step. So it gradually, starting from the initially all queues are initialized to 0, and then some of the queues gradually becoming more and more negative as it learns more and more about the action values, and eventually it converges to the correct value after, I think this is after 7 episodes. That's why I had to put this many episodes in the exercise. Okay, so for the exam questions, I can what I can tell you is that most of the questions will be short, fill in the blank type of questions, plus 1 or 2 questions like this one for computing the V and Q values. So policy-based IR, we're not going to cover it in the exam. Function approximation, yeah, maybe I'll have a few small questions, but it's hard to give a complete example. So I think we can have more discussions.
Can I ask 4 questions about the test time? Is that on the next Monday it will the test will show up in the quiz part, right?
Yeah. In the quiz part. So I think I will. The quiz is not very convenient for this type of calculation questions. So I think I may just give you a Word document because the benefit is that you can work out the equations by typing in the word, right? Otherwise, you have to write on the scratch of paper, on a piece of paper. So it's easier to type in a Word document all the equations. So I think I will give you a Word document by email.
Okay, thank you.
Yeah. So I discussed with Carla, so I think we'll hold a concurrent Zoom session during the exam so that any clarifications you need, you can type or ask in the Zoom. I know that many teachers have this very formal exam proctoring, monitoring, where you have a video camera. They ask students to set up their mobile phone from their back, from the student's back, so that you can see the picture of the student image, video image working alone without any other outside communication. But I think that's too much. We don't have to be so strict. If you really want to discuss with your friend on the questions, I cannot stop you, but I hope you won't.
Xinhua, so we have to check our email to get the exam document, the Word document.
Well, I just put it on my box drive in here. I'll set up a folder that's final exam. Yeah.
Okay. That's on box. Okay.
Yeah.
On box drive. Okay. Where?
Yeah, so as long as you know which content is covered in which lecture, you know, you can do a quick search for the keyword for the questions.
We can use even the find or search property for these files.
You mean in Windows, you can search for the keyword, right?
Yes, exactly.
Oh, yeah, okay, sure. Yeah, you can do that.
But the exam will be in which part of the canvas if I want to pick it? The box? Let me.
So that's where all the lecture slides usually are.
Okay, okay, so there,
Yeah.
okay, okay, that one, okay.
So all the videos are online. So I don't know, what else do we do today?
How many questions in total we are expected to have?
So for a 2-hour exam, this I think we have 30 to 40 short questions plus one larger problem to solve. Yeah.
So 30 to 40 selection questions, guessing question, not guessing, what they call
Multiple
pick the
choice.
right one.
Multiple choice.
Multiple choice 30 to 40 plus one big question that is solving the problem.
Yes.
And what is the division of the marks based on that? The 30, 40 questions, how many marks they have?
So Carla and I have not finalized the exam paper. So I think I think the last question problem may cost maybe 15 to 20 points, and then the rest will cost 80 something points.
So something like 1/5 for the big question and the rest for the multiple choice.
I think so. Yeah.
So 80% to 20% percentage.
Yes, and also in the assignments, we had the 4 assignments. Each is 10 points. So the overall grade of 100 for the final exam will be combined with the lab grades in a 6:4 ratio.
6 to 4.
40% for the labs.
Okay. Okay.
And then if you do lab 5, you get extra 10 points.
Okay.
So if that 10 points exceeds 100 overall, then it's not counted. But it doesn't exceed 100, it helps to increase your grade.
Thank you.
Sure. So do you find this IR stuff difficult? Do you find it hard to work out these equations? It's not so bad, right? Yeah, it's just tedious and error prone. but there's no deep mathematics in it. So
No, I mean, no, the process isn't hard, but it's more about, I guess, understanding like why the equations look like they do, and yeah, stuff like that. But yeah, it's interesting.
yeah, good. Yeah, I know that many engineers in industry, when they learn about reinforcement learning, so they just learn to play with the software packages. So they download the GitHub package, and then they work with DQN, set up the objective function, and then let it run for a few days and get a result. They never go into the details of the equations. So most engineers lack a deeper understanding of the internal workings of the IR algorithms. And that is fine if you're focused on business applications of IR. But if you're more into the research side of IR, you do need to dig into the details and understand how the value-based, policy-based methods work. So it's depending on your career objectives, I guess. So for the imitation learning lectures, I will have a few some short questions. Nothing really difficult. You don't have to dig into the papers. You just everything is on the slides. So I may ask you, if PilotNet end-to-end or mid-to-mid, right? If you attended this lecture, you know. So
End to end.
yes.
Okay.
Yeah, so end-to-end learning is not really very practical for that's why recent research on this topic more focused on mid to mid, or you have the end to mid, right? You start from the raw sensor data and then you end with the planned trajectory. In this case, the affordance affordance, not the trajectory. So that's actually more practical. So it turns out once you have the plan, the trajectory, it's quite easy. The control part is very mature. So you can track the trajectory with a PID controller or MPC controller with no difficulty. So why do you all go all the way to the throttle and steering? It's not necessary. Yeah, so for the Intel RSS, even though it came from Intel Mobileye, it's becoming an industry standard. So it's being standardized. That's why I'm discussing it. So essentially, it helps to assign responsibility in case of accidents. Because it's not feasible or practical to avoid accidents at any cost. Sometimes it's unavoidable, like this. So the yellow car has no way of avoiding the accident if the red car really wants to hit it. So in this case, what you can say as the autonomous vehicle manufacturer is that the accident is not my responsibility. And that's important for the manufacturer. So that's why they defined all the formulas for computing the safe longitudinal distance, and with the proper assumptions of the braking force for the other vehicles and for myself, for the Eagle vehicle, you can compute the safe distance and keep the distance. So there's another lateral distance, which is a little confusing, so I removed that. I only kept the longitudinal distance formula in here. So for the planning, A-star and Dijkstra are the most common planners. So I discussed the breadth first search and depth first search only for comparison purposes. They're not used for planning. And then behavior planner I only mentioned briefly. Local planning is where all the research, all the action is, because the high-level A-star planning is very mature. So generating a smooth path with either spline or spiral. So they're just different forms of equations for the path. So they look really similar from the shape of the curves, but the generation process is a little bit different. So for spline, the path has a closed form equation, but for the spiral, the curvature function is smooth, but the path is not does not have a closed form solution. So artificial potential field is a very intuitive method. You just set up the potential, keep it high around the obstacles, and keep it low near the goal, and then rely on physics to avoid the obstacles and reach the goal. So a dynamic window algorithm So this is planning in the configuration space, meaning that so on the left is the Cartesian space, or so that's the real physical space, x and y axis. On the right is the configuration space, where the xy axis are not xy coordinates, but the angular velocity on the horizontal axis and the translational velocity on the vertical axis. And then all the obstacles have their representation in the configuration space. So this transformation is non-trivial, but you can derive it. So intuitively, you can see that if the robot does a very sharp right turn, it may hit right wall 1. So that's where you have a sharp right angular velocity, almost 90 degrees, and then you may hit a right wall 1. If you have a small angular velocity, and it turns more gradually, and then it may hit a right wall 2. That's a right wall 2 in the configuration space. So it's a very intuitive transformation. So this bicycle model is very important because cars just have 4 wheels, but in terms of kinematics, it's just the bicycle. It's exactly the same. So because the front 2 wheels turn in the same angle and right 2 wheels stay in the same angle, so there's no difference with a bicycle with 2 wheels. And then you can use this bicycle model to update the state. So if you remember derivation of these equations, so this is based on a rotation around the instantaneous center of rotation formed by the 2 wheels. If the 2 wheels are parallel, are both pointing to the front, then the ICR is to the infinity, right? The circle is infinitely large. And then that's where you use the simplified translation motion. But if the wheel is turning a little bit, you need to do the rotational motion, circular motion. Yeah, I think this slide is too much detail. You don't have to really dig into this many equations. So let me put a not covered here. So here, all the red titles indicate the starting of a new subtopic. So the differences among a dexterous algorithm, A star, hybrid A star. So A star uses a heuristic function to guide the node expansion. Dexterous algorithm does not have a heuristic function. So hybrid A star is just to take into account the dynamics of the vehicle so that it's more feasible. So you do not make these unrealistic sharp turns. You make the path smoother. So there's a lot of work on planning, taking into account the vehicle dynamics. So the generated plan or trajectory is easier to track, to follow. Otherwise, you may generate very sharp turns that may be very optimal in terms of finish time or a distance, but it may not be feasible for a controller to track. So for the control part, yeah, PID and MPC are the most common. So for MPC, the main idea is to look forward, look ahead for a time window. So you may have a control horizon and a prediction horizon. They may be the same. Often they're the same, but often you can also have different horizons for control and prediction. So so the bicycle models state up the equation and the derivation of these two equations. So a twiddle is a heuristic approach to a gradient descent approach to tuning the PID controller. Pole placement is a more disciplined approach, but pole placement needs a linear model, whereas a twiddle can be used anywhere for nonlinear systems and for unknown models. So for functional safety, this lecture is really too long. Next year, I'm going to shorten it. There's too many concepts that may not be of interest to many students. So I think in this chapter, the key concept is ASIL decomposition. The idea is that you can decompose a high ASIL system into subsystems with low ASIL to simplify the safety certification process. And also the determination of ASIL based on 3 factors: severity, what's the other? Severity, exposure, and controllability. So I may give you a simple question, say severity is S2, exposure is E4, and controllability is C1, and what's the ASIL level? So it's a table lookup. So this controllability here is not the formal control theory definition of controllability. So it's more of a real life if the vehicle is out of control or within control. So that sense is if the vehicle is is crashing and not within the control of the driver. So all the yeah, and also ASIL is not equal to importance. So maybe a safety function has a low exposure, so it rarely happens, but the severity is very high. Maybe the exposure is driving on the mountainous, snowy road. That doesn't happen very often, so it's assigned a low ASIL. However, its severity may be high, even that is, if the safety function fails, the driver may lose his life. So it doesn't mean that low ASIL function is low importance. These two are not the same. So the introduction, I really should split it up into multiple chapters, multiple lectures. So this thing contains a lot of variety of topics. So the 5 levels of automation. So by now you should understand this picture pretty well. That is the classic modular pipeline. Every box here is a separate module versus the machine learning, deep learning pipeline, where you can replace one or more modules with deep learning. Yeah, so in this course, I did not discuss the perception. So on the one hand, perception is covered in every deep learning course. So the first assignment you do in deep learning is to do the MNIST digit classification, classify handwritten digits into 10 classes, 0 to 9. So that's pretty much the hello world for deep learning. And then you do the ImageNet classification task. So convolutional neural networks. These are not specific, although they're important, not specific to autonomous driving. So I did not really want to cover those in detail. So there's another part of perception that is a SLAM, simultaneous localization and mapping, which I did not cover. SLAM is very important. That is given that your image recognition, your pixel have been processed, and now you need to determine your localization, and perhaps make a map of the environment. So that's called a SLAM. So maybe next year I will cover SLAM more, but not in this year. So SLAM is more common for robotics in unstructured environments, like in indoor buildings. Not so much for really commercial autonomous driving. It's because high levels of automation in autonomous driving often require high definition maps. So once you have the HD maps, as I discussed in this section, once you have this kind of detailed HD maps, there's no need for SLAM anymore. So SLAM is more for unstructured and indoor environments. So hardware platforms. So typically CPUs are not well suitable for computation intensive tasks such as deep learning, machine learning. So people have used GPUs, FPGAs, and ASICs to perform the parallel computation, and use the CPU to run the operating system like a manager of the overall computing system, maybe ROS or AUTOSAR. And then whenever the computation intensive part is needed, it just calls the accelerator, calls the GPU or FPGA as accelerators. So the software platform, AUTOSAR is the official standard. Especially AUTOSAR Adaptive is designed to be the next generation industry standard for in-vehicle computing platform for high performance computing, whereas AUTOSAR Classic is more for the low level, smaller ECUs. So these two are used in combination. So one is not replacing the other. So ROS obviously is very popular, and many autonomous driving companies use it because it offers so many convenient libraries for programming. The drawback is that it's based on Linux and it's too complex and too large. So it's not possible to pass high-level safety certification. So Baidu Apollo used to use RAS, but then they replaced it with their own smaller, thinner operating system and communication middleware, mainly for safety certification purposes. So different sensors, their trade-offs. So LiDAR has a 360-degree coverage, and cameras have you can have different ranges, and radar for object detection, obstacle avoidance, and ultrasound for parking, for obstacles in close proximity, close range. So this article here, this guy I listed is a very good overview of the overall picture of autonomous driving. Yeah, so even though machine learning and reinforcement learning are very popular in research, if you go into industry and look for a job in an autonomous driving company, most likely you'll be working with the modular pipeline because that's the state of the industry. I know that a few companies are focusing on the reinforcement learning approach. This person has a blog that he's Oliver Cameron is the CEO of Voyage. It's a well-funded startup on self-driving cars. So he's always talking about the importance of reinforcement learning, imitation learning. So yeah, unprotected left turn is difficult to program with hand-coded rules. So learning is very important, beneficial for these kind of scenarios. But in general, most jobs in industry are still focused on the modular classic pipeline. So, for example, the Baidu's Apollo and its competitor, the Japanese product AutoWare, they're all based on the modular pipeline, and they're widely used in industry because they're open source. So if your goal is to land a job as a self-driving car engineer, then you should really study the modular pipeline because they are more practical. So security, the main new thing in security is attack on sensors. Other things are pretty mature. So for encryption, decryption of data to and from the vehicle to prevent hackers, that's all pretty well known. So the new research right now is on attacking camera and LiDAR sensors, perhaps GPS. So ethical issues. So as Sebastian Thrun said, ethical issues research is good for philosophers or professors to get tenure, but they're not really of practical relevance. So Sebastian Thrun is the former head of Google's self-driving car project. So his work is pretty much fully focused on the modular classic pipeline. So he does not do machine learning. So he's a very practical guy. So for V2X, mainly you have a cellular V2X, which is basically your phone's 4G or in the future 5G connection to the internet, versus the DSRC, which is essentially Wi-Fi connection. And it looks like the cellular V2X is winning, because the conventional wisdom was that cellular V2X is not reliable and not fast enough. Whereas DSRC, because it's a direct point-to-point connection with Wi-Fi, it's much more reliable. But with the advent of 5G, I think cellular V2X is going to win. Okay, so did I lose most people? Okay, we still have a few people. So that's a very unstructured overview of the course content. So if there's no more questions, I think we can finish today. Yeah, anytime you have any questions, you can leave a message on the discussion board. But the discussion board, I find out that it sends out notifications not in real time. Oftentimes it's by the end of the day or something. So I don't get it instantly. So yeah, in that case, if you have any questions, just send me email.
Thank you so much.
Sure, you're welcome.
Thank you.
So I think I'll also join the Zoom session during the final exam in case you need me to answer some questions.
Thank you.
Okay, I'll see you on
Thank you.
June 1st.
Okay.
Okay, goodbye.
Okay, bye-bye. Thank you.
Thank you. Goodbye.